In this module, we will try to answer the question, what happens when we have more than one minimum or maximum? Let's go back to our very first example of a function with a single decision variable x. For x equals a and x equals d, we have both df over dx equals 0 and d2f over dx squared negative. This means that by our definition, a and d are both maxima. In this simple case, because we're able to plot the function f of x as a function of x, we can easily see that d gives us a bigger maximum than a, and if we are looking at the biggest maximum, d would be our answer. In general, this is not such an easy question to answer. If we go to a two-dimensional example, in this case shown, we have 4 points A, B, C, and D that are all minima, because at all of these points, the partial derivative of the objective function with respect to variables x1 and x2 are 0, and all the second derivatives are negative. So these are all minima, but which one is the smallest minimum? The optimality conditions that we have developed involve only the first and second derivatives, and therefore they are only local conditions. They only consider the conditions around the point where we're trying to find whether it is an optimum, minimum, or maximum. These conditions do not compare separate optima, and therefore they do not tell us which of the various optima we might find is the global optimum. So in general, to find a global optimum, we must find and compare all the optima. So we must find them, calculate the value of the objective function at all of them, and then compare them on the basis of the value of the objective function. Needless to say, in a large problem, this can be quite a task that requires a large amount of computing time, because there may be lots and lots of optima, and it may require so much time that it becomes essentially impossible. Fortunately, in some cases we can make use of the concept of convexity, because it can be shown that if the feasible set is convex and the objective function is convex, there is only one minimum, and it is therefore the global minimum. But I need to explain in more detail what I mean by a feasible set that is convex and a convex objective function. Let's illustrate the concept of convex feasible set with some examples from a two-dimensional space. All of the examples shown on this slide are convex feasible sets. The areas shown in yellow are the feasible set, and everything outside the dashed area is not part of the feasible set. The example on the bottom right extends all the way to infinity in both the x1 and x2 dimensions. By contrast, the examples shown on this slide show non-convex feasible sets. Before going to the next slide, try to figure out what makes a difference between convex and non-convex feasible sets. Here's the answer. In a convex set, if you take any 2 points and join them with a straight line, any point on this straight line is also part of set. So on the upper left-hand corner, I have taken some points that belong to the set. They're actually right on the edge of the set, and I've joined with straight line. You can see the straight line is entirely within the set. The same thing applies in examples on the right-hand side of the slide, and on the bottom left, where we're dealing with a one-dimensional example, and I have taken 2 points that are part of the set and joined them by a straight line, and again, all the points are part of the feasible set, or in this case, the feasible segment. On the other hand, in a non-convex set, there are points of the set where if I draw a straight line between those 2 points, some of the points on this straight line do not belong to the set. So for example, the example on the top left corner, the green line crosses the blue area in the center of the set, which is not part of the set. Therefore, this set is non-convex. The upper right corner example, well, the 2 sets are separate, so if I take a point in each part of the set, part of the line joining these points is going to be outside of the set. The example on the bottom right, the part of the line that goes out of the jaws of this example is outside of the set. It is therefore non-convex. And the 2 examples on the bottom left corner are also quite important. The one at the top, the feasible set, is a set of discrete points along the line. Obviously, because we only have discrete points, any line joining these will include points that are not part of the set. And again, the one-dimensional example at the bottom left, I have 2 separate segments. Therefore, it is a non-convex set because the line joining 2 points in the 2 points from separate segments will include points that are not part of the set. What about the second part of the requirement? The fact that the objective function should be convex. Well, here's an example of a convex function of 1 variable. And here's another example of a convex function of 2 variables. On the other hand, this function of 1 variable is non-convex, and this function of 2 variables is also non-convex. So, comparing the last 4 slides, try to determine what makes a function convex, or how we could define a convex function. Here's the answer. A function is convex if for any pair of points xa and xb, where this function is defined, a straight line joining f of xa to f of xb will be entirely above the function f of x. So for example, if I have a point y, any point y, between xa and xb, I can define y as being kxa plus 1 minus kxb, where k is a scalar between 0 and 1. The function will be convex if k f of xa plus 1 minus k f of xb, which is the definition of the straight line between f of xa, f of xb, xb, if the straight line is entirely larger than f of y, which is f of kxa plus 1 minus k xb. The function shown on this slide is non-convex because I have taken 2 points marked by red dots and joined them with a straight line. The green part of this straight line are above the function f of x, but the red part of the line are below the function f of x, and the function is thus not convex. Convexity is therefore very useful because if we can prove that a minimization problem is convex, and by that I mean proving that it has a convex feasible set and that the objective function is also convex, then this problem will have one and only one solution. And that means that if I can find that solution, I will have found the global minimum. And in fact, when a optimization problem is convex, finding this solution is usually not very difficult. On the other hand, proving convexity is often difficult. It's often so difficult that it's even harder than proving that finding all the solutions of the problem. And double unfortunately, power system optimization problems are usually not convex. So that means there may be more than one solution to power system optimization problems, and that is a difficulty that we will have to deal with. This section provides a brief introduction to nonlinear programming, which is a set of techniques that is used when the optimization problem that has to be solved is nonlinear. The method of Lagrange multipliers that we have studied in some details is very useful because it provides lots of good insight into the solution. Unfortunately, the analytical solution that the method of Lagrange multiplier provides is practical only for small problems. And applying it directly to real-life problems of significant size is simply not possible. In addition, there are difficulties when the problem is non-convex. So we often need to find a solution to an optimization problem when we don't want to do it analytically because it's too large or too complicated, and we only have access to either just the objective function or the objective function and its first derivative calculated at distinct points, or the objective function, its first and second derivatives. Let's start with a very simple one-dimensional problem. Let's suppose that we want to find the value of x that minimizes a function f of x of this single decision variable x. And let's suppose that the only thing that we can do is calculate the value of f of x for any value of x. Well, one naive approach to this problem would be to calculate f of x for a range of value x and then choose the one value of x that minimizes f of x. So let's see how we might proceed with a naive one-dimensional search for an optimum value. Let's suppose we want to find the minimum value of the function f of x over a range of x indicated by the green segment on this diagram. Well, I can calculate the value of f of x for point x and then repeat the process for a whole series of other point x spanning this feasible set. And once I have calculated the value of f of x for enough points on this range, I can go back and find the one that has the lowest value of f of x. Now, this method works, but needless to say, is going to require a considerable amount of computing time if the range is large and if I need a sufficiently good accuracy, meaning I need to choose a set of points x close to each other. The procedure I have just described is quite obviously naive, and much better approaches have been developed. For example, let's repeat the process where we first calculate the value of f of x at one point x naught, which might be the lower end of the range. Then we can calculate the value of f of x on the point x1 and at the point x2. Because the value of f of x1 is lower than f of x0 and f of x2, we have narrow or search range, and if the function is convex, we have bracketed the optimum. We can then calculate the value of the function at x3, which is between x1 and x2. Because f of x3 is less than f of x1 and f of x2, we can say that the optimum is between x1 and x2 if the function is convex, and we no longer need to consider what's between x0 and x1. And then we can repeat the process until we have sufficiently reduced the range of the search in such a way that we have a sufficient accuracy. Note that if we get a function of this type, we could completely miss the optimum because this function is non-convex. This procedure is guaranteed to converge quickly only if the function is convex. That's very nice in one dimension, but what happens when we have many decision variables? The unidirectional search that I have just described is not going to work because it was based on the idea that I was searching in just one direction. And we could generalize the naive search that we discussed before to search thoroughly the feasible set, but that would become quickly totally impossible as the dimension of the problem increases, because the number of points that we would have where we would have to calculate the value of the objective function would increase very, very quickly. But if we can calculate the first derivatives of the objective function, we can develop much more efficient search techniques, because the gradient of the functions gives us the direction in which the function, the objective function, increases or decreases the fastest. Let's illustrate how a multidimensional search might work using a two-dimensional algorithm. This algorithm would be called the steepest ascent or descent algorithm, depending on whether we are looking for a maximum or a minimum. And we would start with a point, or starting point for the search, and we would calculate at that point the gradient of the objective function. This gradient tells us the direction of the steepest ascent or descent of the objective function. Since the gradient gives us the direction in which the function increases or decreases the fast, it makes sense to search along that direction for a point that is going to be a minimum or maximum. So we can proceed with a unidirectional search, not along one of the decision variables, but along the gradient direction. So let's proceed with this search. We start from the point where we were and calculate, or using the unidirectional search algorithm, we look for the point where this function is minimum along this direction. The point where we find the minimum or the maximum along this direction is not necessarily going to be the minimum or maximum of the objective function. In fact, in most cases, it will not be, because the objective function is typically not simple. So what we need to do at that point is calculate again the gradient. And that gradient will tell us in which direction we should proceed, because it identifies a new direction where the function increases most rapidly. So we can perform again a unidirectional search along that direction, and that will give us another point where the function is maximum along that direction. But again, that point is probably not the minimum or the maximum. So we continue. We calculate the gradient at that point. We identify a direction where we need to search, do a unidirectional search along this direction, and repeat the process along the new direction that we have found, and find a new point. Once the changes between two iterations of this process are small enough, we stop and declare that we have found the optimum that we were looking for. This next slide illustrates the process. In this two-dimensional case, I can possibly draw contours that indicate how I move to find this minimum or this maximum. Note that at each point, gradient is perpendicular to the contour of the function at the point. Note that choosing the direction of steepest ascent or descent is not always the best choice, because the direction of the gradient can change rapidly, and there may be a need for a lot of iteration before you find the optimum. Other techniques, more sophisticated, have been used with varying degrees of success. One particular complexity is that the direction chosen must be consistent with the equality constraints. Another problem is how far to go in the direction of a unidirectional search, because those searches can be very time-consuming. People have developed second-order techniques that use information from the second derivative of the objective function to speed up the process, to kind of go directly to the minimum or the maximum in that direction. There are also problems with the inequality constraint, because as we know, there may be lots of inequality constraints in the optimization problem. And if every time we move in one direction we have to check all of these inequality constraints, that could take an enormous amount of computing time. Let's illustrate this problem with inequality constraints using a simple two-dimensional example. Let's suppose that our starting point in this red dot inside the feasible region. And let's suppose that we have calculated the gradient of the objective function at that point and that we have found the direction in which we want to move. The first question that we have to answer is, how do we know that we have to stop at the point where this direction crosses one of the inequality constraints? Now, let's suppose we have solved that problem and that we know that we have to respect this constraint and move along that constraint. The next question is that at some point, maybe we will have to move away from this constraint because it may no longer be binding. One approach to dealing with inequality constraints is to replace them by penalty functions. Let's illustrate how that might work. Let's suppose that we have a variable that must remain between xmin and xmax. Normal inequality constraints, you could look at them as being like walls that you are not allowed to pass. With penalty functions, you replace these walls that are impenetrable by a function that you add to the objective function. So in this case, k times x minus x max squared. So that function will increase as x exceeds x max, and it will increase faster if k is larger. The problem with penalty functions is that it does not ensure that the variables remain within the bounds set by the inequality constraints. So one approach is to progressively stiffen these penalty functions by increasing the factor k to enforce those constraints tightly, in a more tight fashion as we go along in the solution process. Now this turns out not to be a very efficient process, and penalty functions can work, but they can slow down the convergence of the solution. Instead of using penalty functions that are essentially outside of the constraint, we can use barrier functions that are essentially inside the constraint and go up to infinity as the point, as the value of the variable reaches xmin or xmax. Now the advantage of barrier functions is that they will keep the solution within the feasible interval. But as we get closer to the optimum, we want to make these barrier functions closer to the limit. It turns out that barrier functions work much better than penalty functions, and they lead to what's called the interior point methods that are heavily used in power system optimization. A major problem with nonlinear programming is that the solution techniques may not be robust. For example, in the example shown in this figure, if we start from point X, we may end up in solution B, while if we start from point Y, we may end up in solution C. That's because we are dealing with a non-convex problem, and the solution where we end up depends on our starting point. In conclusion, we can say that a number of very sophisticated nonlinear programming techniques have been developed. However, these techniques can be difficult to use because different starting points may lead to different solutions, and some problems will require a lot of iterations and therefore a lot of computing time. And many times, to get a method to work satisfactorily on a particular class of problems, it may need a lot of tuning, adjusting some of the parameters, which is never a desirable feature. This section is an introduction to the optimization techniques that are used for linear problems, and it is better known as linear programming or LP. LP is a very big topic and there are lots of very good books on the subject. We don't have time to go through a detailed introduction to LP, so I will just provide a brief introduction to how it works and first why we use it. So why do we use LP? Well, to start, many optimization problems are linear. And by a linear problem, I mean a problem where both objective function and all the constraints are linear functions of the decision variables. Other problems are nonlinear. That means that the decision variables appear as squares, cubes, square roots in the objective functions or in the constraints. But those problems can be linearized. For example, we can linearize the cost curve by replacing it by a piecewise linear cost curve, and we can replace the traditional AC power flow equations, which are highly nonlinear, by the DC power flow approximation. But why do we want to linearize nonlinear problems? Well, it's because there are some very efficient and robust methods to solve such linear optimization problems, and we want to be able to take advantage of these methods. Before going further, it's probably useful if I give a small example of what I mean by linearization. Let's suppose that we have a cost curve given the cost of producing power as a function of the power output of a generator, and the cost curve I have shown there is obviously nonlinear. Well, we can approximate this cost curve using what's called a piecewise linear approximation, where I introduce two elbow points in the middle of the curve, in the middle of the feasible range of the curve, and replace the curves by piecewise linear segments linking the minimum output to the first elbow point to the second elbow point, and the second elbow point to the third elbow point. This type of linearization usually makes very little difference in terms of total cost, but it can have an impact on the solution because the operating point will tend to congregate at the elbow points or the upper and lower limits of the generator. Mathematically speaking, what does a linear programming problem look like? Well, let's suppose that we have n decision variables xj. We will have an objective function. In this case, let's suppose that we are trying to minimize the sum from j equals 1 n of cj xj. We will have some inequality constraints. For example, we may have m of these inequality constraints, each of which is expressed as a sum from j equals 1 to n aij xj, which must be less or equal to bi. And we will also have some equality constraints. We will have, in this case, I have p of them, and each of these is expressed sum from j equals 1 to n of cij xj equals di. And in these objective function and constraints, cj, aij, bi, cij, and di are all constants. Rather than giving a complete theory of linear programming, I'm going to try to explain how it works in very general terms using a simple example. So let's suppose that we have a maximization problem in a problem with two decision variables x and y, and our objective is to maximize x plus y. We have also a number of constraints. First constraint, and those are constraints that you will find in all standard form linear programming problem, is that x and y must both be greater or equal to 0. In the xy plane, this simply says that our solution has to be in the upper right hand corner of the plane. We have another inequality constraint that says that x should be less or equal to 3, and this constraint in the xy plane is represented by a straight line, vertical straight line at x equals 3, indicating that all the possible solutions have to be to the left of this line. We also have an upper limit on the y decision variables, saying that y should be less or equal than 4, and this is shown by the horizontal blue line and indicates that all the solution must be below this line. Our final constraint is x plus 2y greater or equal than 2, which is represented again by a straight line, like all constraints in a linear programming problem, and the acceptable solutions have to be above this straight line. If you don't know how to figure out whether it's above or below, just figure out what the value of for x equals 0 and y equals 0. In this case, we have 0 is not greater or equal than 2, so obviously 0 is not on the acceptable side of the constraint. So these are all the constraints that we have for our linear programming problem, and they define what's called the feasible region of the problem. So our solution has to be somewhere in this feasible region. And linear programming takes advantage of all these constraints to determine the solution. The objective of our LP problem is x plus y and is also represented by a straight line. On this diagram, x plus y equals 0 is represented by this red line. The fundamental property of linear programming is that the optimal solution is going to be at one of the vertices of the feasible set, or one of the corners of this yellow form that we have on this slide. And what we have to find is a value of x plus y that is maximum, but still in this feasible set, or we have to find the vertex of this feasible set where x plus y is maximum. In this case, maximizing x plus y can be visualized as finding the vertex where the red line is as far as possible from the origin. So let's try to find the optimal solution by progressively moving the red line away from the origin and stopping at every vertex of the feasible set. Our first stop is at the point x equals 0, y equals 1. This is a feasible solution, and the value of x plus y at that solution is 1. But if I move the red line a bit further from the origin, I find the point x equals 2, y equals 0, which is also a feasible solution because it is on the feasible set and it has a higher value of the objective function, x plus y equals 2. But I can keep moving the red line and stop at the point x equals 3, y equals 0, where x plus y equals to 3. And finally, I can move to the point x equals 3, y equals 4, where x plus y equals 7. That is our optimal solution because any other of the vertices of this feasible set leads to a smaller value of the objective function. So how do we solve an LP problem in general? Well, we start with the constraints. In my two-dimensional example, these constraints define a closed area. In the general case of n decision variables or n dimensions, these constraints define what's called a polyhedron in n dimensions. And as I have mentioned before, if a solution exists, it will be an extreme point or vertex of this polyhedron. And the idea is that I should start from any feasible solution of the problem, any solution that meets constraints, and I can go from that feasible solution to the optimal solution by following the edges of the polyhedron, just like I followed the outside contour of my feasible set in my two-dimensional example. Now, in my two-dimensional example, this was fairly easy to do. In more complex problems with more decision variables, more dimensions, I need an algorithm to decide which edge I should follow next. And that algorithm, the best known algorithm to do that, is called the simplex algorithm. To illustrate this last point, let's go back to the two-dimensional example. In this example, I started from point x equals 0, y equals 1, and I found the optimal solution by moving counterclockwise along the edges of the feasible set, and it took me 3 steps to get to the optimal solution. However, I could have gone in the clockwise direction and would have taken me only 2 steps, going from x equals 0, y equals 1 to x equals 0, y equals 4, and then from that point to x equals 3, y equals 4. It would have taken me only 2 steps. In this case, it really didn't make much of a difference to take 2 steps or 3 steps. But if you have a case with many decision variables, as is often the case in linear programming problems, making the right choice in which direction to go is absolutely essential. And that's what the simplex algorithm is good at. However, if the number of decision variable increases and we have lots of constraints, going all the way around the polyhedron that defines the feasible set could take a very, very long time. And a few years ago, people came up with the idea of interior point algorithms, which instead of making their way around slowly the outside of the feasible set, were actually going through the inside of the feasible set. And this has led to the interior point algorithms, which were then shown later to be equivalent to optimization with barrier functions. These little diagrams are intended to illustrate the interior point method. On the left, we would have what the simplex method does. It searches from vertex to vertex until it finds the one that corresponds to the optimal solution. The interior point method on the right, the idea is to go through the inside of the feasible space and progressively tighten the barrier functions so that they approximate better and better the linear constraints. In some cases, simply linearizing a problem does not provide enough accuracy. In those cases, you can use what's called sequential linear programming, which works as follows. You start by linearizing the problem around one operating point. You find a solution using the linear programming approach, and then you relinearize the problem around this solution, and then you repeat the process of finding a solution using LP, and you do that until the relinearization makes no difference to the solution. In summary, the main thing to remember about linear programming is that it has 2 main advantages over nonlinear programming. First, it is very robust. If there is a solution, the LP algorithm will find it. And unlike nonlinear programming, there is only one solution. So there are usually no problem of trying to find a local solution instead of the global solution. The second enormous advantage is speed. There are some very efficient implementation of LP solution algorithms that are available in solvers. So the main challenge for us power engineers is to formulate problems as LP problems and then pass on these problems to these commercial solvers that then deliver a solution. Therefore, many nonlinear programming problems are linearized so that they can be solved using a linear programming approach, which will give a solution and will give it fast.